A big hello and welcome everybody to the ForeWarned is ForeArmed webinar. We've got some great speakers here today. So this is the first of a series of 4 webinars offering a snapshot into the activities and outputs for a new project called ForeWarned is ForeArmed. So this project is working on forecast product development to better equip farmers and agriculture value chains so we can manage the impacts of extreme climate events. So the project's led by MLA, Meat and Livestock Australia, and the ForeWarned ForeArmed project runs for a few years to 2022 and is supported by funding from the Australian Government's Department of Agriculture as part of its Rural R&D for Profit program with cash and in-kind support from 14 project partners from right across Australia. So it's a big collaboration, and these webinars are the halfway point of the project. So the R&D partners will update with insights on the work underway. And today we'll be hearing from Dr. Debbie Hudson and Dr. Harry Hendon from the Bureau of Meteorology to share their work across some of their key forecasting work. So just to introduce myself, I'm Graeme Anderson, Climate Specialist with Agriculture Victoria. We do a lot of extension and communication work with farmers and industry on climate risk, such as the break, climate dogs, understanding forecasts, and I guess we're one of the 14 partners. And we do quite a bit of work here with University of Melbourne and Birchip Cropping Group as part of this project in testing products with farmers. Just some housekeeping. We're really keen on interaction and questions as we go through this. So for people who have joined the webinar, if you scroll, run your mouse over the bottom of the screen, you'll notice a Q&A box that's located at the bottom of the screen. So just move your mouse over it, that'll appear. Click on that box, type in your comment or question, and we'll get to them and bring them up through the presentation. So it's a great chance to ask questions, so please take up that offer. So I think we might move on to introduce our first speaker. So I'd like to welcome Dr. Debbie Hudson. Debbie has over 20 years experience in climate science and is a principal research scientist at the Bureau of Meteorology based in Melbourne, focusing on multi-week and seasonal climate prediction. And she's leading the component of the ForeWarned ForeArmed project that's developing new forecast products around the likelihood of climate extremes on multi-week to seasonal timescales. So over to you to kick off, Debbie.
Thank you, Graeme. And thank you all for taking the time to join this webinar and your interest in the ForeWarned is ForeArmed project. Harry and I are going to tell you a little bit today about the progress in the work packages that we are involved in. And I'm involved in work package 2, but just to give you a bit of an overview of what the project's all about. I think it's a really exciting project because it's a real end-to-end approach. It involves work in work package 1, which is underpinning science, trying to improve our forecast system and interacting with users to define the needs of forecasts on these timescales. Then there's the work package I'm involved with, which is developing forecasts. And then we have our partners that are working on interfacing those forecasts to industry decisions. So things like, when should I harvest? How do I manage my irrigation? And then we have an extension and training component. And as you can see, there are a number of research partners involved in the project, as well as a number of RDCs that are funding it. So first of all, I hope that most of you are familiar with our Bureau Climate Prediction Service. And this is the service that we're trying to enhance in this project. And so specifically, we have forecasts in the upcoming weeks, forecasts for upcoming weeks, months, and seasons on whether or not you're going to have above or below average conditions for rainfall, maximum and minimum temperature. And so one of the key aims of this project is to give you more information in that, more information than just knowledge of whether you're going to get above and below average. So specifically, what we wanted to do is develop a range of heat, cold and rainfall experimental forecast products in this work package. And we make these products, experimental products, available on a research web server to get feedback from users in our reference groups in the different agricultural sectors. And then during the course of the project, we're going to select 5 of those products to become official Bureau forecasts that will be made available on the Bureau's website, in the same website that I showed previously. So the forecasts are not going to be highly tailored products because, as you saw, there are a number of agricultural industries involved in the project. So they will be of broad utility across industries. And the first operational product we expect to be available to the public in March 2021, and the others are going to follow in a staged approach. So now just talking about our research and development, product development, we've done it in a schedule where the first phase we focused on heat extremes, but we also developed a number of products that are generic that address heat, cold and rainfall, and I'll show you what I mean by that later. And then we moved on to adding some cold extremes, and our focus at the moment is on the rainfall extremes. But really, in this project, our products are not static, so we'll go back and add. So recently we've just done another cold extreme product, which I'm going to add shortly. So, but that is the general phased approach for our product development. So I guess to step back, what do we mean by an extremes forecast product? So I guess on the one hand, I'm talking about forecasting what I call climate extremes. So where the weather is averaged or accumulated over a period. And so this is where, for example, instead of just saying, you know, am I going to have above average rainfall for the coming season, what I really want to know is what is the chance of having an extremely dry season, like a decile 1 season, or an extremely hot month. But then we're also looking at actual weather events. So what is the chance that you're going to have more heat waves? Or what's the chance you're going to have a heat wave in the week after next, or a frost event? So I just want to also give you a little bit of background. So the model that we use to produce these forecasts is called Access-S, and it's not a statistical model. It's actually a model like our weather forecasts are based on, that actually is simulating what's happening in the atmosphere every single day. And this little animation here is showing a forecast from our Access-S model, and you can see the contours of pressure, and the blue shaded is rainfall. There's a tropical cyclone coming in. And so the model simulates how the atmosphere, land and ocean evolve over time. And this is what our forecasts are based on. But when we run a forecast, when we produce an outlook, we don't just run one forecast, because there is uncertainty about how the weather will evolve. Even if we had the best model, the perfect model, there's still going to be uncertainty from a thing called chaos. So the way that we address this is by running the model more than once. And so we actually run 100 outcomes or scenarios. And that's where we get our probabilities. So for example, for a particular upcoming season, we're going to run the model 100 times, and we get 100 different scenarios. And if we were looking at a simple one for above average rainfall, so if 80 of those 100 scenarios predict above average rainfall for a season, then we say that there's an 80% chance that you're going to have above average rainfall. So the key thing in this, in these timescales, is that we're talking about things like probability, risk, shifts in the odds or shifts in likelihood. We're not talking about being able to predict a weather event, 20 days into the future. We're not about saying the temperature is going to be 26 degrees in 2 weeks' time. It's all about how risk and what the probability is that there's a change. Okay, so this is just to introduce, this is the web portal that we put all our products on. Our products are listed on the site here. We have some generic products that weren't developed in this project, but we include them here. And then these are the products that we've developed so far in the ForeWarned is ForeArmed project, and we're going to be adding some cold ones shortly. We have at the top here the date at which the forecast started. So this example is from the 17th of October last year. And you can select the variable. So here the variable we're interested in is in minimum temperature. The forecast period, so this is week 2, so days 8 to 14 of the forecast. And then some of the products have output options. So this one, for example, is looking at what is the potential for you to have a frost in the week after next, And here it's frost potential, so it's based on minimum temperature. So the option here is probability of it being less than 2 degrees, and then there are other options. And we have a little question mark here. If you hover over the question mark, it brings up an explainer which describes more about the product that you're viewing. And we also have a feedback button for gathering feedback. And so for these products, as I said, we're looking at multi-week and seasonal timescales, so anything beyond the 7-day forecast up to seasons. So just quickly some notes that basically that website and the products on there is really our research in progress. It's a bit of a brainstorm, but what's novel about it is that you're involved in this brainstorm. You can see it as it evolves, and you can help give us feedback on how it progresses. So the products are for feedback purposes, and we're not really offering them as a service, and so we don't really want them appearing in the media. And it's not static. Products are added and removed. And also this web viewer that I showed you is a research tool. It's not actually how the operational products will be delivered at the end of the project. So, and another thing is that the products should be considered as an initial concept for display. If we select a particular product to be taken further and eventually displayed on the Bureau website, then the look and feel will be enhanced because there's considerable overhead in doing that enhancement at the research and development stage. So, for example, enhancements at the operational stage could improve colors, being able to zoom on maps, better way to select your stations, and accompanying explanations and skill. Okay, so now I'm going to show you some examples of forecast products. I don't have time to go through all of them in this presentation, but I want to give you a sense of some of them. So the first one I'm looking at is, this map over here shows the observed rainfall deciles for November, December, January. That's just passed. And you can see a number of areas that had lowest on record and had decile 1 rainfall season. And this shows you the operational forecast that the Bureau released for the chance of exceeding median rainfall. So you can see that the forecast was suggesting that there was a reduced chance of exceeding the median. But that doesn't tell us whether or not it's going to be an extremely dry season. So what is the chance that you're actually going to have a decile 1 or 2 rainfall season? And that is what this product is doing. So this product is saying, what is the chance that you're going to have a really extreme rainfall season? So this is the forecast for that November, December, January season. And the brown, yellowy brown areas all show areas where there's an increased risk of you having a decile 1 or 2 rainfall season compared to what the normal risk is. Now, the normal risk is 20%. If you think about deciles, deciles are all about 10% intervals, and we're combining 2 deciles here, so that's 20%. So if you look over the past, we're looking at events that climatologically occur 20% of the time. So if you have probabilities greater than that 20%, you're having increased risk of getting a decile 1 or 2 rainfall season. And this is one of these generic products that I said apply across rainfall and temperature, because we can look at, for example, what is the chance it's going to be an extremely hot or an extremely cold, a decile 1 or 2, or an extremely wet season or month ahead. So this is an example again for that same November to January season. This is showing you what was observed for minimum temperature. So you can see that there were large areas that experienced decile 10 minimum temperatures in that season. And this is the forecast. So this is saying, what is the chance that I'm going to have an extremely hot minimum temperature season? And by extremely hot, we mean in the top 20% of events that have occurred. So that's decile 9 and 10. So again, usually you would expect to have that 20% of the time. That's the usual risk. Anything shaded here in color is showing a heightened risk, so an increased chance of having that hotter minimum temperature for the season.
You going to say anything about how impressively good that forecast looks?
Well, that was quite a good forecast. Mm. Well, that's so. I'll come. Actually, that's a good segue, Harry, because a question people often ask is how well do the forecasts perform? And that's a challenging question, and that's not a simple answer, because how well the forecasts perform varies by variable that you're looking at. So for example, we tend to have more skill for temperature than we do for rainfall, but it also varies based on how far in advance you're looking, and also what region. So I'm showing you here as an example. This is showing the skill for forecasting seasons. So I've shown here for forecasting, say, January, February, March, April, May. And this is saying how skillful are you at forecasting decile 1 and 2 rainfall. So aligned with the product I showed you about 2 slides ago. And as you can see, it varies considerably. So, sorry, anything that's in color means that you have better skill than using climatology, which means that you are going to benefit from using the forecast compared to if you just assumed it was going to be like you always have known. So anything in color has skill better than climatology. And you can see that it varies by season. The other thing about this to remember is what we show here is average skill. So we assess this over a large number of years, but skill's not static. And some of the stuff that Harry's going to present is going to show you that depending on what kind of climate drivers are acting, our forecast can be more or less skillful. Okay, so now just to go back to some example products. So I showed you before what is the risk of having a decile 1 or 2 month or season, or a decile 9 and 10 month or season. And I showed you that as a map. And map information is really useful because sometimes you want to have the context, the broader context. For example, you may have stock and adjustment properties, or you may be looking for adjustment, or you may be involved in a value chain and you want to know what's happening in other areas. But this product here is now going to tell us what the risk is like across all of those decile ranges. And this example that I've got here is a forecast for week 3. So that's well beyond the weather forecast. So it's a forecast for the 3rd to the 9th of September last year, from the 20th of August. And I've chosen 3 different areas because they all show quite different forecast signals. So here, for example, in Applethorpe, the climatological bar tells you what I've shown you before, that there's a 20% chance your forecast is going to occur in each of those categories by definition. And then we want to see, well, how is the forecast actually changing those odds? How is it shifting the odds? And you can see that for Applethorpe, it's more than doubling the risk that you're going to have a decile 9 and 10 maximum temperature week. And it's dramatically reduced the chance that you're going to have an extremely cold week. Now, of course, that doesn't mean that you cannot actually end up having one of these, end up having an extremely cold week. All it is doing is showing you the change in your risk profile. Here's another example for Burnie. And now for that week, Burnie actually, the signal was to actually have slightly increased chances of having an extremely cold week. Whereas for Geraldton, it's pretty much suggesting that you're going to have more or less average conditions. But what it is also telling you is that there's a reduced chance of you having extremely cold conditions. So another product is a product that shows your time evolution. So this example is for weekly averaged maximum temperature. So each bar here is for a different week, which we call week 1 up to week 5. And this is for maximum temperature for Sydney at the start of this year. Well, from the 31st of January, so very recently. And what we have is in red, we have the forecast. And in grey, we have the climatology. So basically in grey, it's saying if we look over the past years, what are the ranges in temperature that we would normally expect for that week? And so what we can do with this product is we can compare the forecast, which is in red, with what you would normally expect for that time of year, which is in grey. And these red boxes are there because they're the forecast range from those 100 model scenarios that I mentioned to you. So basically, you run the model 100 times. Each scenario is going to predict a given maximum temperature for a particular week. You rank them all up. The line in the middle shows you what the middle rank is, so that's the median. The 5th percentile, so we don't show on here the minimum or the maximum, we show the 5th value and the 95th. And so that range is coming from those outlooks that you are running. So you can see here the range in week 1 is a lot tighter compared to the range in week 5, and that's typically what we see in forecasts. What you can also see is that in week 1, there's a very strong signal to having hotter than normal week compared to the climatology. That is the median from climatology, and the median for the forecast is considerably higher, as is the whole box. And then you can see in week 2, the signal shifts. The signal here is showing a week of cooler temperatures. And I've just put in here what actually did occur. So this week here was associated with the intense rainfall that we had in February very recently. And you can see this is the difference from normal in temperature. So you can see the reds here are showing that we did indeed in Sydney have hotter than normal conditions in week 1 and colder than normal conditions in week 2. All right, just to end off, I'll just show you a couple more of the forecasts. This is a forecast for week 2. So again, beyond what is available for the weather forecast. And it's showing what is the chance I'm going to have a heat wave. And so here we define a heat wave as 3 or more consecutive days greater than the 90th percentile. So it means it's a hottest day that's in the top 10% of hottest days that you experience for that time of year. And it's 3 or more consecutive days, so it's a buildup of heat. And I'll just show you what actually did happen in that time. So all the areas in yellow and red are showing areas where there's increased chance, where there's a chance that you're going to have a heat wave in that week. And this is actually what did happen in terms of the heat wave status. So this heat wave status is slightly different to this, but it does give you an indication of the heat that occurred in that 25th to 31st of December. And that's the difference from normal in terms of the temperatures. So this forecast actually gave quite a good warning of upcoming heat wave conditions. Similarly, we have similar products for cold. So we have the chance of you having a cold wave. So the chance of you having persistent cool conditions. So 3 or more really cold days in a row. And then we have other ones that are looking at frost. So it's not actual frost, it's frost potential based on minimum temperature. And you can select whether the minimum temperature is less than 2 degrees or less than 5 degrees. So your chance of having a really heavy frost. And then this product here shows you what is the chance of you having at least 1 frost in that period. This product here tells you what's the average number of frosts in the period that are being forecast. So what's next for us? So the first product that's going to go to Bureau Operations is going to be announced, end of March or into April. And then we're going to start doing a deep dive into that product and doing feedback on that, and it will be progressed to Bureau Operations and be available to the public in March 21. We're busy working on our rainfall-focused experimental products, and they're going to be released by the end of March. But the whole time we're going to be continuing to add and update experimental products and continuing to receive feedback from you all on our experimental products to help inform us how we should progress. I think, Graeme, that's it for me. Thank you very much.
Very good. Thank you very much for that, Debbie. So the question and answer box there for anyone that's got any questions for Debbie. Now, we've got one question here, Debbie, from Frank Egan, just saying, when can we expect to see improvement in the 4-month forecast? And also just sort of, I guess you explained a little bit about that, but there's certainly some of the forecast stuff, got the reading of the tea leaves pretty right for that sort of drier at the end of the year. But how do you explain, say, the recent sort of wetter conditions and what seasonal forecast can and can't pick up?
Sure. So I guess, the if you take the recent wet conditions over the East Coast, our forecast didn't really get that much in advance of what you got for the weather forecast. And some weather systems are not going to necessarily be predictable far in advance, whereas others will, because in order for us to be able to actually predict some of those events, there has to be some kind of large-scale driver in the atmosphere that's happening earlier on that will give us that knowledge. Now, and when it gets picked up in the forecast, if that signal comes through in, say, 2 weeks in advance, then we'll get it. But if our forecast is released 3 weeks in advance, then it's not going to necessarily pick up that event. So I think going forwards, the important thing is that just like in a weather forecast, you get issued a weather forecast every single day, or even less, on timescales of less frequently than a day. It's continually evolving. And for example, your day 6 and day 7 forecast can change. And it's the same for this sort of multi-week period, that conditions in the atmosphere change. And so we really have to have the forecast updated on a regular basis. You asked about the month 4.
Yeah, that's right. So I guess that, for some farmers, that's season 3 and 4 months. So do we have any indication, is skill improving over time with those forecasts?
So I guess if you're talking about monthly, so for a seasonal forecast, we tend to have often, if you're going out further, more skill for a seasonal forecast than for a given month. So a seasonal forecast that contains month 4 will be more skillful than an actual month 4 forecast. And again, it's a little bit like what I said previously. For something like temperature, our month 4 forecast can actually be pretty skillful. And again, that also depends on what time of year. So around the springtime shows good skill. But again, something like rainfall is more challenging. So it really depends on the variable and the time of year. We are as part of this project, we are looking at how we can improve the accuracy, and that's an ongoing challenge for us. This is a difficult problem, and it's actually a problem that's being worked on internationally. So we have a partnership with the UK Met Office, and we interact with their researchers there. So innovations that they bring forward, we can take up.
Okay, thank you. And there's quite a lot to do with, it's one thing developing new forecasts, but also making sure we do plenty of work so that we're understanding what forecasts can and can't do. So thanks.
That's right.
There's a couple more questions coming in. That's great. Please keep them coming in. There's some good discussion that we'll be having after Harry's presentation. So speaking of which, as Harry gets his presentation up, I may just introduce Dr. Harry Hendon. So Harry's a Senior Principal Research Scientist at the Bureau of Meteorology based in Melbourne. His research focuses on mechanisms and predictability of climate variability at various timescales and contributes to the development of the Bureau's sub-seasonal to seasonal forecast systems. And he leads the user needs and forecast development part of the ForeWarned, ForeArmed project. So great to have you there today, Harry. So if you could lead us through the next part of the webinar. Thanks.
All right, thanks, Graeme. Okay, so this is about Work Package 1.2, which is this forecast system research, development, and evaluation. The goal of this component is this increased understanding of what's driving climate variability and weather variability and how predictable it should be. And that knowledge then underpins the development of both our models and our products, sorry about that typo, and also the communication about around an extreme service. So for instance, we have a regular briefing, climate catch-up through the community of practice to discuss the current seasonal forecast, where the new findings that we've discovered in this project we talk about. The other outcome of this part of the project is to actually improve our forecast system. So that question just came up, that we're investing in trying to make our models better. It's a long and tedious job to actually make the model better. I think to answer the question specifically, when's the forecast at month 4 going to get better? Well, in Axis S2, we think we're going to have some improvement because we have a new way of initializing the land surface, but we think the really next substantial gain in forecast skill will be when we implement Axis S3, which is probably 2 to 3 years down the track. Okay, and so what's the output of this? So in contrast to Debbie's component, where their output is products, which you can then access on the web, our outputs are primarily reports and publications and briefings, sort of advancing the scientific knowledge of the drivers and predictability of these heat and cold and rainfall extremes. And also those findings then contribute to working on the model errors that are contributing to the ability or inability to predict the extremes. And of course, the other key output then is going to be the actual improvements that get implemented in the model. Okay, so this package is really split into 2 components. There's a part at the Bureau, which I'm involved in, and there's a part at Monash University. So the part of the Bureau, we're really focusing on the prediction science, and that's done with myself, Unpa Lim, and Guomin Wang, though we have a regular input from Debbie, amongst others, and other people at the Bureau. The Work Package 1.2b is the group that's really working on trying to improve the Axis forecast system. And that's based at Monash University, and that's Christian and his postdoc working there. In today's presentation, I'm primarily going to talk about results from our component of the project and not talk too much about progress being made by Christian. So we look at the bottom one first. That's what they've been working on. So they're trying to make the model better. In the first couple of years here, they've developed a really novel way to diagnose systematic model errors. And it's interesting, their approach is they're concentrating on the errors in the depiction of extremes and whether those errors are actually any different than the model error that happens not predicting an extreme. And that's giving a lot of insight into where the errors are coming from. They've also been working on an initial attempt to implement a new scheme in physical parameterization of the model to depict unresolved coastal sea breezes. And so, it's around Australia and through Indonesia, it's very complicated coastlines there. And the model doesn't perfectly resolve the difference between the ocean and the land. And so they've implemented a scheme which can better simulate the onset of sea breezes and land breezes, which then potentially could better depict rainfall around these complicated coastlines, which could be a contribution to the air in the regions to the north of Australia. So the main thing I'm going to talk about today is the top part, is the part we've been involved in, which is the drivers and predictability. And for this talk, just going to talk about the heat extremes. And I'm going to give 2 examples. One is looking at the tropical Madden-Julian oscillations impact on extreme high temperatures in the southeast during the springtime. And the other is a pretty exciting bit of research on polar stratospheric vortex variability and its impact on early summer heat extremes and bushfires. And that's very relevant to what just happened late last year. Okay, for the tropical Madden-Julian oscillation, I guess I've assumed there's a little bit of knowledge in the audience of the MJO as we refer to it, but just as a snapshot, the MJO just refers to this large scale, so thousands of kilometer wide areas of suppressed and enhanced tropical rainfall that traverses slowly along the equator from the Indian Ocean out into the Central Pacific. It's now become conventional to describe the MJO in 8 phases, and it's really based on the location of the rainfall. And so a view of those 8 phases is these series of maps down the left side there. And just our convention is, phase 2 is followed then by phase 3. And so in phase 2, there's enhanced rainfall in the equatorial Indian Ocean and suppressed rainfall to the north of Australia. That pattern then slowly shifts eastward. So by phase 5, there's enhanced rainfall in the Australian sector, and then by phase 8, the suppressed rainfall has moved into phase 8 and 1. The suppressed rainfall has moved into Australia. Because of this slow phase speed and long period of the MJO, there's about 7 days between each one of these phases. So the typical period is about 50 days. And so, yeah, just to remind ourselves, the wet phases over Northern Australia are typically phases 4 through 7. So you can see those green and blue colors over Northern Australia in phases 4, 5, 6, and 7. What's important about the Madden-Julian oscillation is it drives both a direct impact in the tropics. So, you know, if you happen to be in Indonesia or northern part of Australia, you'll directly feel these enhanced periods of rainfall and suppressed periods of rainfall. But it also acts as, the MJO also acts as a source of atmospheric wave activity that can drive a remote response, in fact, all the way to Antarctica. And it excites planetary scale atmospheric waves. So this rainfall variation in the tropics excites planetary scale atmospheric waves and teleconnects the MJO to the rest of the globe. Okay, so what's it look like in our springtime for maximum temperatures? So we can just, for each one of those MJO phases, over the period, say 1990 to 2012, we can just average together all the times that the MJO was in phase 1, phase 2, phase 3, and phase 4. And we're looking now at maximum temperature across the top row there. So you can see we get elevated, enhanced maximum temperatures in phases 2 and 3, pretty much concentrated from Adelaide to Melbourne and even into Tasmania. It sort of peaks in phases 2 and 3. To change that into an impact on an extreme temperature, the bottom plot shows the same information now, but it's just the change in probability of being in the upper quintile, so above the 80th percentile. And you know, the odds are more than doubled in phases 2 and 3 to have a heat extreme when, as the MJO is in phase 2 and 3 across the southeast of the country. I'm not focusing on the other 4 phases, but they pretty much look the opposite. So while these phases favor enhanced temperature extremes, the other 4 phases favor, not having high temperatures or even cold extremes. But we're interested just in the temperature extremes. So it's an interesting question of why we get that signal across the southeast. And so I've just repeated that composite there in the top plot there of what the temperature anomaly looks like across Australia in phase 2. The bottom plot gives you an insight of why that's happening. Now it's a little complicated plot. Above the blue line is the shaded regions there are the rainfall anomaly in the tropics. And so this phase 2 composite is when we have suppressed rainfall across the Indonesian region and enhanced rainfall in the central or western equatorial Indian Ocean. The bottom half of the plot is some measure of the circulation in the troposphere. This happens to be the stream function at 200 hectopascals. The gray colors are for cyclonic circulation. Let's see, does my arrow work? Yeah, so cyclonic circulation, so going around clockwise. And the orange colors are anticyclonic circulation. Oh, sorry, I got it backwards there. The orange colors are anticyclonic and the gray colors are cyclonic. And so you can see when we are in phase 2, well, for one thing you can see there's sort of this pattern of wave motion that you can trace all the way into the southern hemisphere. It starts out to the northwest of Australia. Puts an anticyclone in the bight over Australia, a cyclone down there in the Southern Ocean, another one, all the way to South America. But the key is for Australia is we get anticyclone in the upper atmosphere, just sort of centered just to the west of Tasmania, right? And so the vectors are not the wind, so just disregard the vectors. But you can imagine we've got anticyclonic circulation here, so we're going to have northeasterly winds, which are going to be promoting these high temperatures. Okay, so this is the key, that what we're seeing in the south part of Australia is not the direct response to the MJO. It's the fact that the MJO is initialized or instigated this wave train. Okay, so a question we might ask is, well, how well does the AccessS forecast model simulate the chances of being in these warm conditions when the MJO is in phase 2? All right, so the observed composite is the plot there on the left. And then we can just take, using the hindcast during the spring, we can just pick out all the times the MJO was in phase 2 and then make a composite with the model data. And you can see it, and I didn't show the first week. The first week pretty much looks identical to the observed, but by the second week, you can already see a problem. You can see that while indeed we get the right sort of signal in the east part of the country, we're getting too much positive anomaly in the southwest corner. And then you go to the third week, and that pattern sort of looks the same, but it's not as strong. And then by the fourth week, you get, the pattern's even shifted more. It's weaker, but even shifted more to the west. Okay, and I'm going to try to convince you in the next plot that this is stemming from biases in the model. And the main bias we think this is coming from is the model's depiction of the convection in the Indian Ocean and in the subtropical jet, which lies over Australia. Okay, so I'm not sure if this plot's going to go over very well for this audience, but I'm just going to walk you through it. So if we look at week 3 in the forecast, and we look at the bias in the model, and I'm looking at the top two fields here. One is the outgoing long wave radiation, which is some indicator of enhanced rainfall in the tropics. So where the OLR is low, you get more rainfall, and where it's high, you get less rainfall. And we're looking at the bias. And so the bias in the model is, you get these distinctly blue colors in the Western Indian Ocean and red colors to the northwest of Australia, which means the model's making it rain too much in the Western Indian Ocean and not rain enough in to the north of Australia. Okay, and then the plot below it is the bias, or the mean air in the model for the east-west winds, or the west to east winds at 200 hectopascals, so in the upper troposphere. And you see very distinctly the winds are too weak, so there's a negative anomaly over central Australia, and that's right where the subtropical jet normally lies. And the winds are too westerly to the south of Australia in the mean. Now, one effect that this bias in the winds have is on how the wave driven by the MJO is going to propagate. And the bottom plot is some measure of the impact of how the waves are going to propagate, or the air and how the waves are going to propagate. If you have a physics background, this is something like an index of refraction. So this turns out to be the stationary Rossby wave. But the key thing is that the red colors to the south of Australia mean that these biases in the winds are going to favor too much wave propagation sort of to the southwest of Australia and even across southern part of Australia. And so what we think is happening with the MJO, where the MJO is going to try to propagate a wave confined to a pretty narrow region and put an anticyclone over southeast Australia. These biases in the winds mean that you get too much wave propagation too far to the west. And so this whole pattern of MJO wave train is shifted too far to the west. Okay, and so this is a real challenge that we know, these biases in the model are reflected then in biases of how the MJO makes temperature anomalies in the eastern part of the country. Okay, so another way to look at this then is, well, if the MJO is either weak during the forecast or strong during the forecast, does that make a difference to our forecast skill? And so the measure we're looking at here now is a success ratio, which is the number of times that we were forecasting the temperature to be in the upper quintile divided by the number of times we forecast that plus the number of times, we forecast that correctly divided by plus the number of times that we forecast that incorrectly. Okay, so it's the hits divided by the hits plus the false alarms. Red is where the skill is high and white is where there's no skill. So each column is for week 1 of the forecast, week 2, week 3, week 4. The top row is for when the Madden-Julian oscillation is weak at the start of each one of these weeks. And the middle row is for when the MJO is strong at the start of each one of these weeks. And the bottom row then is the difference. So how much difference in skill is there if the MJO is strong compared to when the MJO is weak? So at week 1, we already know we make a pretty good forecast. This is essentially a weather forecast, so the whole map's red. We make a pretty skillful forecast for temperature pretty much everywhere. But even in week 1, we still see that when the MJO is strong, there's enhanced predictability in the southeast, which is this reflection of where the MJO has a big impact. Week 2, that's even more dramatic, because as the skill drops off in week 2, you retain skill better in the southeast where the MJO has a big impact. And that's still retained in week 3, though it's not quite as dramatic as week 2. But, it's sort of disappointing. By the time we get to week 4, we still think we can make a prediction of the MJO, but we're not getting any enhancement of forecast skill in the southeast. And we think this is this reflection of biases, both in the mean state, but also biases in the MJO. Okay, so this summary then about this component on the MJO and its relation to heat extremes. It's clearly the MJO is an important driver of heat extremes in our springtime in the southeast primarily. It's also a source of multi-week predictability of heat extremes. Currently we have good skill with Access S1 to about 3-week lead time when the MJO is strong. So, you know, if we're monitoring things, the MJO is strong, we should have more faith in our forecasts out to week 3 for predicting heat extremes in the southeast. But there's also model biases, both in the mean state and in the depiction of the MJO, and I didn't actually show those, but there is biases in the MJO, and that's clearly limiting predictability. So we think there's really untapped predictability, especially at weeks 3 and 4, which can be realized if we can resolve some of these outstanding model biases. So it's not saying that's an easy thing to do, but there should be hope. Okay, now I'm going to change gears and talk about the polar stratospheric vortex and its impact on surface climate and predictability of surface climate. And just for a brief summary of what the polar stratosphere, what this vortex looks like, the plot on the left, the contours on the plot on the left are of the contours of the zonal wind averaged around 60 south. And the plot goes from the surface, which is about 1,000 hectopascals, up to the top of the stratosphere, which is 1 hectopascal. And the key thing you see it runs, you know, I've broken it up so that it's centered on essentially the middle of winter. So it runs from April through to, you know, June, July, September, and then back to March, through to March. And what you see is that the vortex develops every winter, and it's strongest sort of right after the peak of winter. So it's strongest in July and August in the upper stratosphere. And I don't have the contours on here, but these are about 100 meters per second. So it's a very strong vortex that circles around Antarctica in the upper stratosphere during our winter. But then as the sun comes up over the South Pole, those winds weaken. In fact, by the time we get to our summer, the vortex is broken down completely in the upper stratosphere, and you actually get easterly winds. The shading is the standard deviation of the winds using annual data or each year's data. And the important thing about that is all the heavy shading is happening in the transition from the really strong westerly winds to the breakdown of the vortex. And it's happening sort of in our springtime down into our early summer. Okay, so that's when this vortex is most variable. Now we've used a mathematical method to try to extract the sort of the leading mode of variability of this year-to-year variability of the vortex. And this is depicted on the right here. So it's the same map layout. It runs from April through to March and from the surface up to 1 hectopascal. But now this is what a typical variation in the stratosphere might look like. And so the shading now is for negative wind anomalies where it's blue and positive wind anomalies where it's orange. So typically we might see an early onset of the vortex in the upper stratosphere, say in June and July, that then results in a very early breakdown by even a month earlier of the vortex in the upper stratosphere in September and October. And then this thing couples down or it continues down to the surface and has sort of its peak response at the surface in November and December. Okay, and some measure of this mode of variability is this time series at the bottom here. And so there's one value of this thing every year. And the sense of this is when it's positive or in red, it has the sign of this anomaly. So it means the vortex broken down early. And what's really outstanding here was what happened in 2002. So if you're a fanatic of the stratosphere, you would have known that in 2002, we had a very early breakdown and rapid warming of our vortex. So it's really the first time we've ever had a really major warming of the polar stratosphere. That's 2002. But you can see there's other years where there's other times where when vortex is broken down earlier than normal. But conversely, also the vortex can break down later than normal. Okay, so why do we care about this breakdown of the vortex? And the reason is because you can see it couples all the way down to the surface. So when the vortex breaks down early in September and October, we tend to have easterly anomalies in the higher latitudes from October through to December. And that's indication of this so-called southern annular mode, where the southern annular mode is shifted into its negative phase. So the The winds became, less westerly at high latitudes, but more westerly in the mid latitudes. And then that then has direct impacts on climate in Australia, and especially climate extremes. And so when we picked out all those years where we had an early breakdown of the vortex, we then looked at the chances or the probability of occurrences of temperature, rainfall, and bushfire weather extremes during October through January. And what you see is this pretty pronounced signal concentrated in the east and then down the east coast for maximum temperature. Consistent with that, there's also drier conditions, increased chances of extreme dry conditions sort of in the central east. And this forest fire danger index is also highly elevated, and especially down the coastal strip. So it's high in the central east, but also out to the coast and then down the coastal strip, past Sydney. In terms of quantifying this, it's these changes in probability are more than a 4 times enhanced risk of temperature in the upper, I think I'm showing quintile, yeah. Temperature above the 80th percentile, rainfall below the 20th percentile, and this forest fire danger index above the 80th percentile. Okay, so as we did for the MJO then, is this stratospheric variability then some source of predictability of surface climate? And so we've done the same thing as for the MJO. We've looked at all the times that the vortex weakened early, and it turns out in that time series, in our hindcast period, we have 5 years where the vortex weakened early versus 18 years when it wasn't weakening. And we're looking at the success ratio to predict extreme temperature being in the upper quintile. So it's the number of correct positives divided by the correct positives plus the false alarms. And this is for October through January mean maximum temperature when the forecast was initialized on the 1st of September. So it's a long lead forecast. And what you see is, yeah, indeed, when the vortex weakens, we have very much improvement in forecast skill just in those regions where I highlighted where we historically see an impact of the vortex on the surface temperature extremes. And it's much improvement in forecast skill in those 5 years compared to the other 18 years. Okay, well, what about this year? Just to remind you that if you saw anything in the press that we put out, that we had a very strong 2019. We had a very strong warming of the vortex and early breakdown of the vortex. One way to visualize that is showing the height field between 60 and 90 south, and this plot runs from 700 hectopascals up to, I think that's 10 hectopascals. So these are the heights over the poles. So you can think of this as temperature as well. So and this plot runs from the 1st of September through the 1st of January. So sometime in late August, near the 1st of September, we had a rapid onset of warming and breakdown of the vortex. It pretty much stayed in the stratosphere until mid-October. And then it coupled down strongly to the surface. And if you just look at this time series of the Southern Annular Mode Index, it didn't show much sign of the stratospheric warming until about the 17th of October. And then the Southern Annular Mode stayed in its negative phase pretty much continuously until the end of December. And it turns out this, in the record we have back to 1960, this is the most negative mean value of SAM for October to December that we have on record. Okay, in terms of this other, this mode of variability that I described early on, which we call the troposphere coupled mode index, I've now updated this through 2019, and so you can see what actually happened this year is actually slightly stronger than what happened in 2002. So this very unusual event. The 2002 was, some people viewed it as like once in a 50-year or once a 100-year event, but now we've had an even stronger event this year. And it was highly predictable. So if below this lower panel here is how well our access model is predicting this index. The blue is the verification, which is based on the area interim reanalyses, and the yellowy orange color is the forecast of this mode using Access S1. And so that first part is just the hindcast set. And in fact, that hindcast set, when we initialized on the 25th of August from 1990 to 2012, the forecast skill is remarkably good. It's 0.8. But that's actually what we forecast on in real time on the 25th of August this year, 2019. So it verified remarkably well. We actually forecast the strongest event ever compared to our hindcast set, and that's actually what happened. In terms of what actually happened locally in Australia, yeah, if we look at the T-max decile map for November 2019, it looks remarkably like this composite of what you would have expected from having a breakdown of the vortex. And our forecast, of course, was really, as I already commented to Debbie, because it's a similar thing. Our forecast of the temperature is pretty, it was pretty remarkable agreement, because even with this low SAM signal, we would expect it wet and cold in Tasmania, and we picked that up quite well. In terms of what it meant for the bushfires, Debbie says, hurry up, I'm hurrying. This is my last slide. In terms of the bushfires, this slide was provided by Mark Parrington from ECMWF. This was the number of bushfires accumulated from the 1st of October through the 25th of November, so it's a little out of date, but the really high concentration of bushfires out at the coast. There's just a snapshot on the 1st of December just to emphasize that these things were occurring in westerly winds, really unusual westerly winds because of this negative SAM. And this was the New South Wales fire. It really peaked in November, but they actually went into December. In terms of the total number of fires in that region, if you just sum them between the 1st of September and 24th of November every year, there's the time series for the last 2003 to 2018, and that's what would happen this year. It was just off the charts. Okay, so yeah, polar stratospheric vortex variability is an important driver of our southern hemisphere climate variability, but especially extremes for subtropical Australia in our spring and summer. I'd say it's as important a contributor of predictability as is IOD and INSO. The access model well predicts the evolution and especially can make the connection to the surface. Now, what happened this year is rare. It happened before in 2002. So I think more work is needed to understand what controls their occurrence. But and there's got to be windows of opportunity to make have more confidence in your forecasts, like we did this year. But but when they do happen, we should take advantage of it. I would say we've done ongoing work now by looking at the impacts of, well, this weakened vortex also reduced the ozone hole in the stratosphere, but by reducing the ozone hole, there potentially is a positive feedback onto the weakened vortex. The model right now doesn't have time evolving ozone, so it's a future area of improvement. It's probably not something that we actually have the capability at the Bureau, so we're going to have to rely on our partners at the Met Office, but it's certainly more motivation now that we should be going down that path. Okay, Graeme, that's all I have to say.
Very good. Thank you, Harry. An amazing insight there, which sort of takes us right into what's happening behind the scenes in terms of understanding the models and also improving any sort of little biases in the model so that it leads to improving forecasts for Australia. Because if we don't sort those issues out here, then then no one else will do that for us. So thanks very much. Fascinating to hear about both the MJO and the stratospheric warming. So we've got a few questions that are coming in now. We are a little bit, we've gone a little bit longer than we'd anticipated. So for those that need to leave at 2, feel free to leave. This will be recorded and the questions will be kept, but we will just ask a few of those questions for those that are interested and want to continue. So one question is just with regards to things like Southern Annular Mode and MJO and Indian Ocean Dipole. So when we see a seasonal forecast, so basically what's happening behind the scenes of those other climate drivers, they're captured in the current forecast outlook?
Yeah, as Debbie said, the model we run is a comprehensive model that is essentially a global weather model that we just run out to 6-month lead time. And so all of these modes of variability are operating. Sometimes they have more impact than others, but they're all captured in the model.
Very good. And I think that's one of the parts of understanding forecasts is if the forecast is saying one thing, it's hearing that commentary behind what's behind that. Why are you thinking that it's heading that way? And I guess that's that was certainly part of that spring discussion. So we've got a question here from George, and is the outlooks integrated with climate change trends in the forecasts?
Yes, so they are, because there's two ways that the climate change trend gets into the forecast. The key way the climate change trend gets into the forecast is in the initial condition, primarily in the ocean initial condition. So we know the oceans have warmed up over the last 50 years, but those changes in the amount of heat that's in the ocean are captured in the hindcast and in the forecast. We also have, we've evolved the carbon dioxide forcing in the model so that it is, I'm not sure which trajectory we're on or scenario we're on, but it doesn't really matter. But the hindcasts are based on a time evolving as observed carbon dioxide forcing, and then the forecasts then project what this carbon dioxide should look like in the future. So it's climate change impacts are included in two ways, both captured in the initial conditions and in we evolve the carbon dioxide in the atmosphere. Okay,
so basically the forecasts are reading the live physics of what's happening out there at the minute. So which it's just that there's this warmer trend over time. So
yeah, and I should say the model actually does predict the trend really well, even though maybe that's not a very hard thing to do. It's not a hard fence to get over. But if you look at the trend, the observed trend, and you look at the trend that the model forecast, there it's pretty good agreement.
Okay, very good. Thank you. And these questions are for you both. So Farmers for Climate Action, when looking at August, September, October rainfall, how far in advance do you think you may have a product for this? And similarly for IOD.
Well, maybe Debbie will say more, but I would say, you know, that's the season that we have the best skill in the eastern part of the country. And, you know, right now, I mean, our operational forecast is only for the next season, even though we do run the model out longer than that. But we do have, you know, skill better than climatology for that season for a large portion of the east part of the country. In terms of the IOD, once we get into an IOD, the IOD is pretty predictable. Trying to predict the onset of the IOD is not so predictable. We don't do as good a job. But by the time you get into, you know, August, September, October, typically the IOD is already commenced, and so the skill is pretty good.
Very good. Thank you.
Say anything more?
No, you said it well.
So that's sort of when the best skill for the year. Is that your observation?
Yeah, certainly for the south, the east, and the south.
Yeah.
So the oceans have shown their cards when we get to our sort of.
Well, I think it's more than that. It's the fact that if you just look at when El Nino and the IOD are having its biggest impact across Australia, it's those seasons, and that's where the impact's the biggest.
Very good.
But it's true. Good. The oceans have shown their cards then, so it's a combination of both.
Thank you very much. Now we've still got a couple more questions rolling in, if you're okay. There's a question from Neil, and just after some clarification about the week 1 forecast in this project compared to the existing public bureau forecasts. You able to clarify how that's dealt with?
So the week 1 forecast that we've been showing in our products here comes from Access S, so our seasonal prediction system, whereas the weather forecast that you get comes from a different forecast model that's focusing specifically on forecasting the upcoming 7 days, and it operates at a much higher resolution, so much finer scale than our model. So we haven't, and I guess the focus for this project was beyond that week 1 timescale, but it doesn't preclude that we might be able to do some forecasts where we show an average of the week 1 conditions, like I showed in that time series plot.
Yep.
But I would say a really key piece of work going forwards is to look at how we can, we at the Bureau can integrate our weather forecasts from day 1 through to the next second week.
Yeah, okay. I would say that, and the week 1 forecast is interesting because we run it with our model, which is slightly lower resolution, or I shouldn't say slightly, it's lower resolution than the Bureau's numerical weather prediction model. But we use the Bureau's numerical weather prediction model, atmospheric initial conditions. So we're using the same initial condition that they use for the weather forecast, but we stick it into our lower resolution model. But on the other hand, we have it coupled to the ocean. We haven't done the comprehensive evaluation of what our forecast skill looks like in week 1 compared to the higher resolution numerical weather prediction product the Bureau makes. I would expect they better have better skill than us because they're running a much higher resolution model, but I don't think it's going to be a different planet because we're using the same atmospheric initial conditions and we're using the same model and model physics, just different resolutions.
Yeah, so a lot of this using the Model EXSS is about getting some heads up around the multi-week or the sort of the 3-monthly if there's anything significant showing up, and then when it comes to individual events, that's where the local bureaus weather forecasts are the place to go for trapping it within the next 5 days, that sort of thing.
And I mean, as Harry mentioned, with our XSS, we actually have a full ocean model running. So like I showed the animation of the atmosphere with the fronts going through, I could have shown you an animation of what's going on in the ocean. And we have to have that for the longer timescale forecast because of something like El Nino and how key the ocean is to determining what's happening at those longer timescales. So our weather forecast model doesn't actually have that ocean component in it.
Okay, very good. All right, thank you. Now Peter Heyman has asked Harry, sorry if I missed it. You showed spring, September, October, November. Does the MJO have similar or less impact on predictability of maximum temperatures in summer?
Yeah, we didn't show summer. It has a similar similar impact. It's not as concentrated in the southeast like I showed. There's something really unique about how concentrated the impact of the MJO is in the southeast in the spring. So the impact in summer is not as strong as in spring, but it's in a similar, sort of across the southern part and southeastern part of the country.
Very good, very good. And a question from Deb: is there anything we can anything we can do for feedback to help the project along?
Well, so I showed you, for example, if any of you are actually looking at the experimental products and while you're looking at them, you have a question or you have particular feedback, you can actually click on that feedback button that's associated with the products. But equally, our partners like Peter and Anne-Marie and Richard and yourself, Graeme, are running reference groups and having webinars where there's the opportunity to discuss these products. So I would just encourage you to have your say and help us understand what might be useful for you, and also what you don't understand, because sometimes we've looked at a lot of these things many times over and you kind of forget that maybe the first time you looked at it, it wasn't obvious. So a large portion of, as we decide a particular product is going to go to operations, a lot of the work will be on how we can actually make them more easy to understand. This whole business of probability space is quite confusing, and we want to try and improve our communication around that.
Yeah, that's right. And there are a lot of partners involved in the project and a lot of opportunity for discussions. And if anyone has any further questions on the project or wanting to have input, Anne-Marie has put up the slides there, just showing the contact for the project. Now, there's 3 more webinars that are coming throughout the year, which will be talking about various parts of this national project. So there's a lot of good detail to get into. Any queries there, please just drop an email to Russell Pattinson, who's our Fearless project leader. And I'll just finish with the final question for the speakers from the Bureau. When is it that you actually have more confidence in an outlook? What sort of things are you seeing when you have more confidence in an outlook?
I'll go first.
Definitely go first.
I would say it's when we look at an outlook and you maybe see a particular temperature or rainfall signal, but then when you also see what it's predicting in terms of the drivers, so maybe in terms of El Nino or IOD or the stratospheric warming, and if if it makes sense, basically, if we can understand why the forecast might be doing what it's doing, that leads a certain amount of credibility to the outlook. It makes sense, basically.
Yeah, probably as you know, Graeme, because we do the briefing once a month. We get pretty excited when, as Debbie said, when these drivers become extreme. And whether that's a record strength in-geo event, or a record strength Indian Ocean dipole, or record strength stratospheric warming, we get cocky, right? But probably rightly so. So yeah, so personally, yeah, I have a lot more confidence when the things that we know are providing predictability have a really strong signal. And it's essentially a signal to noise, because you sort of think, well, the noise is constant, but the signal can get big now and then. And
yeah.
So
this
spring we were highly confident of what was going to happen.
Yeah, that's right. And I think that's a part of, like, an important part of the project is there's one thing about improving forecasts, but a really key element is for those of us reading and listening to forecasts is understanding that. And sometimes there's a lot more going on behind the scenes, which increases confidence in an outlook. And sometimes there's not a lot to go on. So I think that's part of how we communicate that. And so that farmers can use that, knowing when there's more confidence in forecasts. So I think that's just about it. Oh, hang on, there is another question coming in. So for those that are still there, so there was a question about where or getting access to the experimental products, because that's actually not on the current BOM public website. So that experimental product that you showed, Debbie, is behind the scenes. So it's there's access to that for research partners. So if anyone wants to find out a bit more about that, then I'd drop an email to Russell Pattinson there. And David Cobon, hello to everyone there in Queensland. And March, April, May school very good in Northeast, surprising because this period is ENSO predictability gap comment. So I'll ask that again, Harry. March, April, May skill is very good.
Yeah. So you could have, in one of the skill plots that Debbie showed, you could see that. Yeah, and I have to say, I don't fully understand that. We've sort of talked about it. We need to go back and investigate that better to understand what's going on. I mean, we sort of got a general understanding of why forecast skill drops between the spring and the summer in the north. We don't have as much skill in the north. We understand that just from how El Nino typically evolves and what's going on with the oceans to the north of Australia. But why it sort of then pops back up with high skill over a pretty wide area of northeastern Australia, I don't know. So we need to think about it.
Okay. Yeah. Just there was a question here with George's question earlier on, was just about asking about integration of climate change trends, but was also asking, when comparing to recent events, did you pick up any of the extreme flood, temp or drought events? And is that a key part of the project of going backwards to work out how many of these were forecast and how will the models do that?
Are we specifically talking about the floods we just had in sort of coastal New South Wales and southern Queensland? Was that?
No, well, I think throughout there was probably a few examples of some extreme from last year. So is that part of how you build confidence around the forecast, by looking at those previous extreme events and then how well were they forecast in the XSS?
Yes.
Yes.
Yeah. We've done that lots of times. We haven't really got going yet for the, I only had a quick look at what was going on with the recent floods, and I couldn't see that there was much predictability beyond about a week.
Yeah, that's what I said.
But we do that a lot. For the big floods we had 2 years ago, last year.
The February
floods, yeah. There's been a lot of work done on that.
And we also run the forecasts over a period in the past. So we do look at events in the past in that.
Very good. Yeah, that's right. I mean, I guess that's where behind the scenes, a lot of people don't realise that all of this is done on the history to make sure that it's where has it predicted events well and where hasn't it. So thanks so much for those insights. It's certainly a very detailed issue, and that's what's good. There's a lot of different key parts to the project. So there's contact details there. This recording from the webinar will be available on the Primary Industries Climate Challenges Centre website next week. I'd like to thank University of Melbourne and Anne-Marie Graeme for organising the webinar, and we'll look forward to catching up to everybody again with those next 3 webinars. So that's it from me. Have a good day. Thanks everyone for joining.